So at last we come to the chapter on applications of integration. It's been a long time coming. We have methods for finding antiderivatives. Those are important because the fundamental theorem of calculus tells us that to calculate a definite integral, the nice thing to do is produce an antiderivative and then use that to evaluate the definite integral. We haven't looked at many applications along the way. We've looked at kind of mass on a rod of variable density. We've looked at area under curves. We've looked at some small examples, but this chapter is just going to be full of applications. We're going to start with something relatively easy, and the applications will get more complicated as time goes on. So in this section, we're just going to talk about displacement and distance traveled in a straight line. So what's the problem? So a straight line, we're just talking about an object that's moving in a straight line. And just like in differential calculus, we assume we've laid out a coordinate axis along that line. So we have a notion of positive direction, a negative direction, the origin, and we have positions at each point along the line. So let's suppose we have an object moving along a line that we've marked off as a coordinate axis, and we let P of t equal the position of the object at time t. I'm going to assume that P is differentiable so that we have a notion of the velocity function, and I'm going to assume the velocity function is continuous so that we can integrate it, so that we know it's Riemann integrable. So let V of t equal dp dt, or what's the same thing, P prime of t. Be the velocity. So, well, there's no let, I should say then, but I'm assuming this exists so that P of t is actually differentiable, that it equals the velocity of the object at time t. And I'm going to assume, we assume V of t is continuous. All right. Then, so what? What do you get from this? Well, then the fundamental theorem of calculus, the fundamental theorem tells us that the integral from a to b of v of t dt, well, it tells us that, well, v of t, we're assuming it's continuous. So the fundamental theorem tells us that this equals, we need to produce an antiderivative of the velocity. But the position's an antiderivative of the velocity, right? Something whose derivative is the velocity. And so the fundamental theorem tells us this is P of t evaluated from A to B, which means it's the position at time B minus the position at time A. But this change in position of an object is called the displacement. So this equals the displacement of the object. Between times A and B. Understand what displacement means. It's this net change in position. So there's no telling what you did in between. Maybe at time 0, I'm standing here. At time 1 minute, I move over there, and at time 2 minutes, I come back here. Then what's my displacement between time 0 and time 2? If at time 2 I end up back where I started? 0. Doesn't mean I didn't go anywhere in between. This is just the net change in position. between those two times. All right, that's the displacement. By definition, displacement is the change in position. And you get it by integrating the velocity. We don't know necessarily the position at time A or the position at time B. We just know the change in position. So what's an easy example? So an example, actually there was a particular one that I wanted. I would like to look at example. Suppose we know the velocity. Suppose v of t is 3t squared minus 12t plus 8 meters per second, where t is in seconds. Okay, so suppose you're given that velocity function. We can ask a whole bunch of questions, but I'm going to ask 3. What is the displacement of the object? I'll just say the displacement. What is the displacement between times 1 and 3 seconds? So there's one question. Times. Or between times, I also want to look at between times 2 and 4 seconds. And finally, I think I'll look at between times 1 and t seconds. So we want the displacement between time, an arbitrary time t, and 1 second. So your net change in position. All right. How do you do these things? You integrate the velocity function. So the displacement between 1 and 3 seconds. This will be the integral from 1 to 3 of our velocity function. So that's the integral from 1 to 3 of 3t squared minus 12t plus 8 dt. By the fundamental theorem, you want to produce an antiderivative of this. It's just the power rule 3 times. So we will get t cubed minus, 12 times t squared over 2. In fact, maybe I should do this in another step. This is 3 times t cubed over 3 minus 12 times t squared over 2 plus 8t. And we need to evaluate this from 1 to 3. This is t cubed minus 6t squared plus 8t evaluated from 1 to 3. And I deliberately picked this so that this polynomial factors nicely, because I did that so that something interesting happens, or I think it's interesting. You get that polynomial factors as t times t squared minus 6t plus 8. And then we need to evaluate from 1 to 3. But you should see that this factors as t minus 2 times t minus 4, evaluated from 1 to 3. So what do we get? You plug in t as 3, so we get 3 times 1 times minus 1, minus what you get at 1, which is 1 times minus 1 times minus 3. So we get a minus 3 minus plus 3. So we get minus 3 minus 3. We get minus 6. Minus 6 what? Don't forget the units on the definite integral. It's these units times those units. This is in meters per second. That's in seconds. This comes out in meters. Well, it's a displacement. It needs to be a change in position. So this is minus 6 meters. Understand that what the minus sign means. This isn't distance traveled. We'll get to that in a minute. This is the displacement, minus 6. What it means is you had a positive direction and a negative direction. And wherever you started at time 1, so here you are at time 1, this is the positive direction, this is the negative direction. At time 3, you ended up minus 6 units away from this. That means 6 units, but in the negative direction. So you ended up over here somewhere, if this is the negative direction, where this distance is 6 meters, but in the negative direction from where you started at time 1. So great, so that's the displacement. What's the displacement between times 2 and 4 seconds? Well, all you do is change this to a 2 and this to a 4, so that's all that happens everywhere. 2, 4, 2, 4, 2, 4, 2, 4, 2 and 4, and then what you get, as opposed to what we got between 1 and 3, between 2 and 4, well, it's one of the reasons I wanted to point out that this factor is like this. When t is 4, when you plug that in, you get 0. When t is 2, you plug that in, you get 0. You get 0 minus 0, you get 0 meters. So between times 2 and 4, the displacement is 0. That does not mean that the object didn't move during the times, all the times between 2 and 4. It means that it just ends up back where it starts. It's wherever it is at time 2, it's back there again at time 4. So the net change in position is 0, but it could have done lots of things in between 2 and 4. In fact, we'll see more clearly what it did later. All right, what if you want the displacement is between times 1 and t as a function of t? What changes there? Well, a couple of things. So we change this, of course, to displacement between 1 and t seconds. And then you put a 1 here, and you put a t up here. Now, in some books, and I believe it's fairly common in engineering, they would leave a t here and have a t as one of the limits of integration. This is actually, there's nothing exactly wrong with it. Recall that this is a dummy variable. It doesn't matter what you call it. We could call it banana. It doesn't matter. But it looks a little confusing to have t in here and the t up there. So usually, when we have a variable in the limits of integration, we don't use that variable for the integration variable, so for the dummy variable of integration. Technically you can, but in practice it just confuses things too much. Although maybe you'll consider this more confusing because, well, that's confusing. Well, you'd consider this more confusing because we'll just change the dummy variable of integration to anything we want. I'm not really going to use banana because that takes too long to write, but I am going to use just a z because it doesn't matter what we use in a definite integral. And so I'm just saying we'll change these to z's. I'll say it again. In a lot of places you'll see the t both is the dummy variable of integration and is one of the limits of integration. It's just a good way to get confused. So I'll change this to a z, oh, not that, 8z. But this is now a 1. This is a t. So what do we get? We get z cubed minus 6z squared plus 8z evaluated from 1 to t. And so what we get for the displacement as a function of time. Between times 1 and t, we get, this is, you plug in t for z, you get t cubed minus 6t squared plus 8t minus what you get, when you plug in 1 for z, which is 1 cubed, so 1 minus 6 plus 8. So this is 3. So we get t cubed minus 6t squared plus 8t minus 3 meters. If things are working right, I should agree. Here, this was the displacement between times 1 and 3. This is between 1 and t. So if we plug in t as 3 here, we better get negative 6. You can check. You plug in t equals 3, and you get 20. It's not factored anymore. So we get 27 minus 9 times 6, so that's minus 54, plus 24 minus 3. So this is minus 54 plus 24, that's minus 30, so minus 3 minus 3, minus 6. Yay. Yippee, math works again. All right, so that's the displacement. It's easy. You integrate the velocity from one time to another to find the displacement of the object between those two times. What if we wanted the distance traveled, though? You know, what if, okay, yeah, we know if the displacement's 0 between times 2 and 4, between times 2 and 4, maybe you went over there and came back. And then, so there's some distance traveled, you just don't see it from the displacement. How do you find, instead of displacement, how do you find distance traveled? So distances don't get counted with plus and minus signs and cancel out anymore. It's so what about distance traveled? Some people say the total distance traveled. Well, let's look at two cases and then say what happens in the general case. So if we knew that the velocity were positive for t in the interval from a to b, then, well, then the displacement, if your velocity is always positive, your displacement would be the distance traveled, because you just keep heading in the positive direction on your axis. Then the distance traveled equals the displacement, so it's just the integral of the velocity. All this says is if you head in the positive direction and you never turn around so that your velocity never comes back and is in the negative direction, then yes, the displacement and the distance traveled are the same. What if your velocity is always negative, or less than or equal to 0 for t in AB? Then you're always headed in the negative direction. Well, then your displacement's going to be negative, because you're always headed in the negative direction. But your distance traveled would be negative that displacement, right? Okay, so yeah, if you're heading in the negative direction, okay, maybe your displacement is negative 6. But that means you traveled 6 units in the negative direction, so your distance traveled is 6. So what this says is then the distance traveled is negative the displacement, but we could move that minus sign inside this integral. Why we might want to do that I'll say in a second. But so this is, instead we could negate the velocity and integrate that. If v of t is less than or equal to 0, then negative v of t is greater than or equal to 0. So we're integrating something greater than or equal to 0 here. So if v of t is greater than or equal to 0, to get distance traveled, you integrate just v of t. If v of t is less than or equal to 0, to get distance traveled, you integrate negative v of t. It means in either case, whether v of t is greater than or equal to 0 or less than or equal to 0, what you can do is integrate the absolute value of v of t. Right? Because if v of t is positive, then v of t is the absolute value of v of t. If v of t is negative, then the absolute value of v of t is negative v of t. So what we're seeing is that regardless of whether the function is positive or negative, and it could be positive on some subintervals and negative on others, it doesn't matter. To get the distance traveled, this equals the integral from a to b of the absolute value of v of t dt. So that's the difference, and it may seem small, but it's actually makes things much more complicated. We'll see that in a second. But as far as the notation goes, notationally it's not much more difficult. You want to find the displacement between times a and b, you integrate the velocity. You want to find the total distance traveled, you integrate the absolute value of the velocity. It doesn't seem like it's that big a deal, but it is, and I'm going to do an example related to the example we did with displacement. After I make a comment, which is, why don't we go ahead and look at the distance traveled. So what is the distance traveled between t naught, so I'm thinking some initial time, and just, so that's a constant, and t, where this is a variable. Well, as we did in our displacement problem, where we wanted to integrate from 1 to t, I'm going to change the dummy variable in the definite integration to a z. So this would be the integral, let me call this, let's call it something, let's call it r of t equals the integral from t naught to t of v of z dz. Okay, why am I bothering to say this? Yes, so the distance traveled between some initial time and arbitrary time t, you integrate the absolute value of the velocity. Well, because we actually can use the first part of the fundamental theorem of calculus, the part we don't use very often. If r of t is defined by this integral, then the first part of the fundamental theorem says that, and I remind you that I was assuming the velocity is continuous. I'm still assuming that, which means the absolute value of the velocity is continuous, which means the fundamental theorem does apply here. Then dr dt, the derivative of this integral function, remember the first part of the fundamental theorem, even though we don't use it very often, it just means you get this integrand with the t in it. It means dr dt is just the absolute value of v of t. Why am I telling you this? Because it means that we have two competing notions, well, conceivably competing notions of speed, and this tells you that they agree. What am I talking about? The speed at which you're traveling. It ignores the direction. It's just, for motion in a straight line, you should know The instantaneous speed is just the absolute value of the instantaneous velocity. So this quantity is the speed. So what you're integrating here is the speed. And what this says is you can define the speed in two different ways. So this is the speed of the object, instantaneous speed. And what this says is it's irrelevant whether you consider the speed as the absolute value of the velocity or if you consider it the instantaneous rate of change of the distance traveled. Either way, you get equal quantities. So yeah, speed, instantaneous rate of change of total of the distance traveled or absolute value of the velocity. Doesn't matter which one you use when you're thinking of speed. Not really, however, having said that, when you talk about the average speed is not frequently the absolute value of the average velocity. For instance, if in our example a minute ago, when the object its displacement was 0 between time 2 seconds and 4 seconds. So its displacement was 0 over a 2-second time interval. So its average velocity is 0. You take the change in position divided by the change in time. But the change in position was 0. Change in time was 2. 0 divided by 2, 0. So the average velocity is 0. But the average speed, we'll see this in a minute, is not 0. If you actually went somewhere and came back, then you were actually moving. So your distance traveled, there is some distance traveled, it's not 0. And so your distance traveled is non-zero, and you divide by 2, and so you'll get something non-zero. Average speed need not be the absolute value of the average velocity. That's only true if your velocity is always positive or always negative. But if it switches signs, then there's some cancellation in the displacement that you don't see in the distance traveled. So what does that mean? It means that it's probably best to think of speed as the instantaneous rate of change of distance traveled, because the average speed is the average rate of change of distance traveled. And if you want instantaneous whatever to mean the limit of the average rate of change of whatever, then you should be taking the average speed, so the change in distance over the change in time, as your notion of speed, so that your instantaneous speed, probably the better way to think of it, as the instantaneous rate of change of the distance traveled with respect to time. But it equals the absolute value of the velocity. So, all right, I've beaten that enough. Let's look at why the total distance traveled calculation is so much worse than the displacement calculation. So, let's find what is the total distance traveled by the object between t equals 2 and t equals 4, and I should have said that I'm once again back in the case of the previous example, where v of t was 3t squared minus 12t plus 8. So I'm back in this example. Between times 2 and 4, we saw the displacement was 0. But we're going to see that the total distance traveled is not 0, and so the average speed is not 0, even though the average velocity is. All right. So what do you have to do? Well, we know what you do. The distance traveled is the integral from 2 to 4 of the absolute value of the velocity. You integrate the absolute value of the velocity. So the speed, you integrate the instantaneous speed from 2 to 4. Great. Well, how do you do this? Yeah, it's one thing to have nice notation that says, oh, this is what we want to do. It's something else entirely to actually do it, to calculate it. So how do you calculate this? How do you integrate absolute values? I want to warn you about a big mistake that people make here. It's horrible, but people do it all the time. We want to find an in theory, what you'd like to do is find an antiderivative of this integrand and apply the fundamental theorem. We know how to find an antiderivative without the absolute values. Does this equal, the answer is no, but I'll put a question mark for right now. Does this equal, you just take the absolute value of what you get when you antidifferentiate this, which is t cubed minus 6t squared plus 8t. Do we just take this absolute value and then evaluate it from 2 to 4? Right? No. The answer is no. Absolutely not. You just can't integrate that way. You don't have a rule that tells you that, oh, you want to find an antiderivative of the absolute value of something? You find an antiderivative of the something and then take the absolute value. This is a horrible mistake. Do not do this. All right, great. There's something not to do. What do you do? Well, when I was deriving how you get distance traveled by integrating the absolute value of the velocity, so by integrating the speed, I said, oh, if the velocity is negative here, well, then the distance traveled is what you get if you integrate negative the velocity. And if the velocity is positive, it's what you get when you integrate just the velocity. Well, and then I used that the absolute value gives you either one of those cases. So we have a nice compact way of writing an integral that gives us total distance traveled. You integrate the speed. But really, in practice, when you go to calculate this, you have to go back to what we said when we were deriving. You have to split this integral up into pieces, into different intervals. You have to split the integral up along intervals where the velocity is positive and where the velocity is negative. And then where the velocity is positive, the absolute value is just the velocity. And where the velocity is negative, you negate the velocity to get the absolute value. So what am I saying? We need to know where 3t squared minus 12t plus 8 is greater than or equal to 0, and where it's less than or equal to 0. And then we'll split up the integral into these pieces and replace the absolute value. In this case, we'll replace the absolute value of this quantity with just this. If this is negative, so less than or equal to 0, then the absolute value of this quantity is negative this. And then we'll use that, we'll integrate that. All right, how do you tell where a function's positive and where it's negative? This is a continuous function. Continuous functions can switch signs only at places where they hit 0. So we find where this function is 0, and then we check in between the zeros and see whether the function's positive or negative. So where does 3t squared minus 12t plus 8 equal 0? Well, use the quadratic formula, which, yeah, we expect you to know. So you get t is, you think, negative b, so negative negative 12, plus or minus the square root of b squared, that's 144, minus 4 times a times c, that is minus 96, all over 2a, which is 6. This is 12 plus or minus the square root of 48, over 6. You can pull a square root of 16 out of here. The square root of 16 is 4, so you get plus or minus a 4 times, left with the square root of 3 over 6. I'm going to write this as 12 over 6 is 2, plus or minus 4 over 6, so that's 2/3. So 2 times the square root of 3 over 3. So this is where this quantity hits 0. Of course, we're doing this for t, we're only looking at t's between 2 and 4. So at what t values between 2 and 4 does 3t squared minus 12t plus 8 equals 0? Well, let's see. Certainly if you subtract this positive quantity from 2, you're below 2, so you're outside the interval, but 2 plus 2 times the square root of 3 over 3, that will be greater than 2 and clearly less than 4, since the square root of 3 over 3 is less than 1. So the only 0 we have to worry about in here is 2 plus 2 times the square root of 3 over 3. So we are splitting up the interval from 2 to 4 at 2 plus 2 times the square root of 3 over 3. And we need to know, is this quantity positive or negative between 2 and 2 plus 2 times square root of 3 over 3? And is this quantity positive or negative between 2 plus 2 times square root of 3 over 3 and 4? You just check. In fact, these aren't points where this function's 0, so we can just check the value of this quantity at 2 and 4. At 2, we would get, so when t is 2, we get 3 times 4, so we get 12 minus 24 plus 8, that's minus 4. So that's negative. So the v of t is negative between 2 and 2 plus 2 times square root of 3 over 3. What about in here? Well, we can check at 4. When t is 4, we would get 16 times 3, you get 48 minus 48 plus 8. You get v of 4 is 8. So yeah, the quantity, the velocity, is positive in that region. So how does this mean we calculate our integral? We split the integral up. We look from 2 to 2 plus 2 times square root of 3 over 3, and from 2 plus 2 times square root of 3 over 3 to 4. We have to split the integral up. As you can see, already this is much more complicated than calculating the displacement. You have to find where the function that's in the absolute values, so where the velocity is positive and where it's negative, and you have to split the integral up there. This really shouldn't be surprising. You can't kind of magically get the distance traveled unless you know when the object was headed in the positive direction and when it was headed in the negative direction. That means you have to know where the velocity is positive and where it's negative. It's not really surprising that we have to do this. It is annoying, but it shouldn't be surprising. So we are still trying to calculate the integral from 2 to 4 of the absolute value of 3t squared minus 12t plus 8 dt. And what we've just found is we should split this at 2 plus 2 times the square root of 3 over 3. So, and I'll go ahead and write it with the absolute values in it one more time, but then we'll get rid of the absolute values in a second. And you integrate from 2 to 4 here, the same quantity. The point is, you can always split up integrals like this, right? It's a theorem. You want to integrate from 2 to 4. You can instead integrate from 2 to anywhere you want between 4. Or actually, it doesn't even have to be between 2 and 4. But you can go from 2 to anywhere you want, as long as you then add to that the integral from wherever that was to 4, so that you think, I went from 2 to somewhere, and then I went from the somewhere to 4, so in the end I go from 2 to 4. And then you just write the integrand both places. You can always do this, but normally this would give you 2 integrals in place of 1, and it would just make extra work for you. But you need to do this where your definition of the function changes, or where your ability to apply your integration rules, like here, changes. We don't have a rule for how you integrate absolute values. But what happens? On this interval, now that it's split up like this, on the interval from 2 to 2 plus 2 times square root of 3 over 3, we saw that this quantity was negative, the quantity in between the absolute value signs. That means that its absolute value is negative this. And between 2 plus 2 times square root of 3 over 3 and 4, we saw that the quantity in the absolute value signs is positive, but that means it's its own absolute value. And so we don't need those. Then you need to anti-differentiate both of these. It's the same anti-differentiation both times, except this one has a minus sign, so it's not like you have to do a lot of extra work. So what do we get? We get what we got before, which was the t times the t. We already anti-differentiated this. And without a plus c, we got t times t minus 2 times t minus 4. But now we'll have this minus sign hanging out in front. And you'll evaluate this from 2 to the nasty 2 plus 2 times the square root of 3 over 3. And then you have to add to that. Well, you take an antiderivative of this, but we know that's t times t minus 2 times t minus 4. And it's evaluated from 2 plus 2 times the square root of 3 over 3 to 4. And we have to evaluate both of these. Now, at this lower limit of integration, when we plug in 2, we'll get 0 because of this part. At this upper limit of integration over here, when we plug in 4, we'll get 0 here, and so we'll get 0 for that part. And you might hope that, oh, look, here's a minus sign, here's a plus sign. We plug in 2 plus 2 times square root of 3 over 3 twice, here and here, but this time with a minus sign, that time with a plus sign. They must cancel out and we get 0 again. No. You have to be more careful than that. That's exactly what doesn't happen. They do not cancel out. You actually get twice the contribution. They don't appear with different signs. Here you'll get a minus, this quantity with that n. But remember, this is the lower limit of integration. Here it will be minus again because you subtract what you get when you stick this in. So you actually get the same quantity twice, and it won't be 0. So what do we get? All right, you plug in the top limit of integration and subtract what you get at the bottom. I'll say it again, when you plug in the lower limit of integration, so when you plug in 2 here, you get 0. So we just get what you get when you plug in 2 plus 2 times the square root of 3 over 3. So we get that this equals, minus 2 plus 2 times the square root of 3 over 3 times 2 plus 2 times the square root of 3 over 3 minus 2 times 2 plus 2 times the square root of 3 over 3 minus 4, and then you get what you get from the other part. But when you plug in the 4, you get 0, and then you subtract what you get when you plug in the 2 plus 2 times square root of 3 over 3. You get this exact quantity again, so I'm just going to write that we get minus 2 times this. Yuck. Well, you can get out a calculator at this point. I am going to simplify this by hand just because it's good algebra practice. But this is the answer. Of course, our question is it 0? The answer is no, but let's see how much we can simplify it by hand. We get a minus 2. Here the 2's cancel, so we get a 2 times the square root of 3 over 3. So I've taken care of this part and this part. if you look at this and look at this, here you have a 2 minus 4, so we can write that as minus 2. If you think of this written kind of in the other order, it might look more like something you're familiar with. This is this plus 2. So we have one quantity plus the other one, and then multiplied times that same quantity minus the other one. That's how you factor the difference of squares. So this equals, so this times this is actually the first thing squared minus the second thing squared, squared minus 2 squared. So we get minus 4 times the square root of 3 over 3. And then here you get times, all right, you get 4 when you square that, 3 when you square that. So 12 over 9 minus 4. 12 over 9 divide by 3, that's 4/3. This is 12/3. So that's minus 8/3. So we get minus 4 times the square root of 3 over 3 times minus 8/3. The minus signs cancel. So we get 32 times the square root of 3 over 9. 32 times the square root of 3 over 9 meters. Right, so certainly not 0. In fact, it's, well, very roughly, the square root of 3 is between 1 and 2. So this is between 32/9 and 64/9. So actually, this is more like, this should be around 6 meters, I think. But the real point is, it's not 0. And it's not particularly close to 0. So that while remember what this was the total distance traveled between times 2 and 4. One of the things you should get out of this is calculating total distance traveled is painful compared to calculating displacement. But then again, there's a lot more information there, so it's hardly surprising. We got the change in position, so the displacement between times 2 and 4 seconds was 0, but the total distance traveled is 32 times the square root of 3 over 9 meters. So the average, it's worth mentioning that the average velocity, so the average velocity between t equals 2 and t equals 4 this is 0, right? Because it's the change in position divided by the change in time. The change in position was 0. But the average speed between t equals 2 and t equals 4 is the change in total distance traveled. So the distance traveled between times 2 and times 4. So it's the distance traveled in that time divided by the change in time, which is 2. So divided by another 2. So this divided by 2. So 16 times the square root of 3 over 9 meters per second. And generally, if someone asks you what your average velocity is, if you're not in a math class, you're not in a physics class, you're not in an engineering class, an average human out on the street says something about, oh, what's your average velocity during your trip or something, they probably want to know your average speed, not your average velocity. On the other hand, maybe it would be weird for them to think that you backed up during your trip, so the distinction between the two might not be there. But typically, average speed is something that ordinary, everyday person out in the street cares about more than your average velocity. They don't really, the fact that you undid some of your your motion by going backwards doesn't come into what the average person means when they're talking about such things. All right, in the next section we will continue with things that are fairly easy. We've talked about area under curves and above the x-axis and area above curves and under the x-axis. In the next section we're going to talk about just kind of the area trapped between two curves. As we'll see again, absolute values will come into the general formula that we write, but that means when we actually go to apply the formula, you have to break things up into cases where the thing inside the absolute values are positive and where they're negative. So we'll do that in the next section.